Here's some hints on how to do problem number 7 from the homework we have this week. Problem 7 describes a system where there's two charged rods in close proximity to each other, sort of parallel like this. One is made out of glass and one's made out of plastic, which really isn't any consequence other than they're both insulators here. They both have 10 nanocoulombs of charge on them. This one is positive 10 nanocoulombs. This is negative 10 nanocoulombs. They're placed 4 centimeters apart. What it wants is the electric field at distances 1, 2, and 3 centimeters between them. So if we draw a line sort of connecting the two rods like this, that might be at 1 centimeter, that might be at 2 centimeters, that might be at 3 centimeters. They'd like to know the electric field at these points here. So obviously the 2 centimeter mark is right in the midpoint right there, but that's just one of the points along the way they'd like to know. A couple things we can get out of this equation, out of this particular problem here, is one, is you should just probably get into your head and know now that the electric field outside of a line of charge, as we sort of got in class here, is K lambda L H divided by the square root of L over 2 squared plus H squared. This is the electric field for a line that has a charge density lambda on it. Remember, lambda is charge density in units of coulombs per meter here. And so this is the electric field outside of the line, a distance h from it. So you can see that this is sort of the equation we're going to use to solve this problem here, because each one of these points here is certainly a particular distance from this line and from this line. So they'll have different h's depending on which distance you're talking about. And if you look at this problem again, once again, it is going to be an electric field superposition problem, because at this particular point right here, say, for example, there's an electric field coming out of this positive line charge going through this point. And so we can denote that by a little arrow, say, that looks like this. And there's also an electric field going through this point, going into this negatively charged rod. So there'll be another electric field through the point like that. So to find the answer to the problem, you need to do a superposition of this electric field from the positive rod and this electric field from the negative rod to see what the answer would be. I find the problem actually easier to look at if we sort of imagine head-on like that. So here's the positively charged rod going in and out of the sheet of the paper. Here's a negatively charged rod going in and out of the sheet of the paper. A line connecting them would look like this, and that point right there might be the 1 centimeter mark that the first part of the problem asks for. So there's 1 centimeter there. This will be 3 centimeters here, 4 centimeters total. So what is the electric field at that point right there? Well, like we drew in the figure above, there's an electric field going that way due to the positive charge, and another electric field that way due to the negative line. I think it said charge, but I meant line of charge. Line of charge here, this is the electric field due to this line of charge. This is the electric field due to that line of charge, all going through that point. What is the superposition? I think 2 applications of this equation here will probably give us the answer here. In particular, you can say something like the total electric field will be that due to the positive line charge plus that due to the negative line charge. And I've already set my signs in here. It looks like both electric fields point towards the right, so I'm calling this positive and that positive, and I'm not going to let any other signs interfere with this sign convention in the problem here. And so, of course, E total here can be something like K lambda L divided by, now for the positive line charge, this particular point is 1 centimeter from it, so there'll be a 0.01 there times the square root of L over 2 squared plus 0.01, that quantity squared, in the bottom. So this is the electric field contribution due to the positive line charge, this little arrow right here. But now we know we have the negative in there, so we'll have to go ahead and add that in as well, and there'll just be another K lambda L divided by, but I am now 3 centimeters from this point, this line charge here. If I'm 1 centimeter from this one, I'm 3 centimeters from this one. So 0.03 times the square root of L over 2, that quantity squared, plus 0.03, that quantity squared. So there you go. This is essentially the answer to this problem here, the electric field at 1 centimeter from the positive line charge. Or, of course, 3 centimeters from the negative line charge. A couple more things, though. I think you can probably work with the numbers there to get your final answer. What are you going to put in for lambda, the charge density, for both of these things? Well, we know that that lambda is defined as Q over L. It's a charge density. How much charge is spread over how much length here? And we know there's 10 nanocoulombs spread on each line charge here. So there's 10 nanocoulombs, and each line charge is 10 centimeters or 0.1 meters in length. So if you put all this stuff in here, I actually get that the lambda, the charge density, both of these rods are charged with here, is something like 1 times 10 to the minus 7 coulombs per meter. Okay, so this is the charge density on either rod. Now it's tempting to say, well, this is the positively charged rod. its charge density must be positive, and this is the negatively charged rod, so its charge density must be negative. But I'm going to be careful with that. I'm only going to use the absolute value of the charge density in this case here, because remember, I've already sort of indicated the direction of the electric field with this sign convention. So if you put a negative sign in for this lambda here, for the negatively charged rod, you will be saying mathematically that this little red arrow actually points the other way, and that's going to give you an incorrect answer for this problem. So we'll leave it at that.